Welcome to section 7.5, multiplying and dividing radical expressions. Alright, so example 1, multiply and simplify as needed. Okay, so what do we have? Well, we have the root 5 being multiplied to this binomial. So let's go ahead and do the multiplication. We'll go ahead and distribute that root 5. So we get root 5 times 2 minus root 5 times root 7. Now, one thing to note, if we ever have a number, we usually put it before a radical. Why is that? Well, because if somebody wrote this, it's hard to tell, if I'm reading that, if that's supposed to be 2 root 5, or if that's supposed to be root 52. Just because the radicals, sometimes people don't always write it far out enough, or maybe they write it too short. So if you ever have a number or any variables, usually put it in front of the square root. Alright, a bit of a sidetrack, but let's go ahead and keep simplifying. So we have 2 root 5 minus, well, they have the same radical, so we can go ahead and do 5 times 7. 2 root 5 minus, and that is just going to be, those two are both prime. So that's going to end up in a prime radical, root 35. And that's it, we're done. We can't simplify anything further. Now, let's go ahead and take a look at the next one. Well, we have sort of a trinomial here, and then it's being multiplied. So let's go ahead and distribute in to each of the 3 terms. And we get 2 root x times 4 root 2 minus 2 root x times the cube root of 4 plus 2 root of x times 2 square root of x. Alright, let's go ahead and combine the terms. So the ones that aren't in radicals, I'll go ahead and multiply those together. And then I'll go ahead and combine the radicals. So 2 times 4 is going to be 8, and that'll be root 2 times x minus 2, and then, ooh, notice our 2 radicals have different indices. Okay, that's a square root and that's a cube root. So we're going to have to go ahead and create a common denominator for them, because that is x to the half power times 4 to the third power. And then plus, and we have 4. Ooh, those are both squares. Even though the 2 is there, remember, technically there is a 2 there. These are just 2 different ways to write the radical. Once again, radical x is the same thing as the square root of x. Those both mean the same thing. It just got to the point that we use the square root so often, it's easier to just drop the 2 instead of always having to write it. Okay, so that's going to end up being the square root of x squared. Just waiting on my pen. Okay. Now what can we do? Well, we can just rewrite this. This is going to be 8 root 2x minus, now we needed to make the same denominator for these guys. So go ahead and times it by 3 because I'm trying to make a denominator of 6. And I have 2x 3 over 6 times 4. 2 over 6 plus 4, ooh, and that square cancels with that square root, and we're just left with x. Alright, almost done. We're just going to go ahead and keep simplifying these guys. Okay, so that is going to be rewritten as, let me just write this down because that's good, minus 2, and this will be x to the third power, and this is the 6th root times the 6th root of 4 squared plus 40x. Once again, remember the power is the number on the top, and the indexed one is the number on the bottom. Okay, so now they have the same radical. Because of that, now we can finally combine them. We get the 6th root of x to the third power, and 4 squared is going to be 16 plus 4x. And we can't simplify any of our radicals any further, so we're done. The hardest part on this one was remembering how to combine radicals when they have different indices. Okay, let's go ahead and move on to example 2. Multiply and simplify as needed. Well, in this first one we see, we have a binomial times another binomial. So this means we're going to have to use FOIL. Let's go ahead and do that. First ones, so that's going to be root 5 times 2x, and then outside 2 root 5 times root 5 inside 4x times 2x, and then last 4x times negative 2 root 5. Whew, accidentally squished into the other one. Let me just move this over real quick. There we go, so I'm not using as much room. Okay, so let's see, what can we simplify? Well, I know that this is going to equal 2x root 5, nothing I can do there, minus, oh, and I can combine these, that's going to be 2 root 5 squared, plus, and then that'll just be 8x squared, plus, and now I can combine the 4 and the negative 2, so that'll actually be a negative 2, or negative 8, sorry, negative 8x root 5. Anything else I can simplify? I always look at the radicals. This is simple, no radical here. Ooh, I can simplify this radical. That square root cancels with this square. And so what do I have? I have 2x root 5 minus 2 times 5 plus 8x squared minus 8x root 5. I can still simplify that further, so I get 2x root 5 minus 10 plus 8x squared minus 8x root 5. And that looks like it's it. Our radicals are simplified, nothing else to multiply. We're done. Let's take a look at the next one, B. So we have two binomials, which means we need a FOIL. But before we do that, notice something. The first two terms are the same, and the last two terms are the same. The only difference is the inside sign. These guys are conjugates, which means when I FOIL them out, I'm going to end up with the first value squared minus the second one squared. So let's go ahead and do that shortcut. So the first one is 5, and the second one is the cube root of 4. So that's going to equal 25 minus, I'll go ahead and rewrite it as 4 squared. So that'll be 25 minus the cube root of, and what is 4 squared? That is 16. Now, can we simplify 16 and a cube root? Are there any perfect cubes in 16? Let's check. 16 is 2 times 8, and 8 is 2 times 4, and 4 is 2 times 2. Do I see the same factor written out at least 3 times? I do. I have 1, 2, 3 2's with 1 2 left over. So I can rewrite 16 that way. So that'll be 2 to the third power times 2 to the first power. So that's the first power, and these guys were written as 2 to the third. Alright, so I can rewrite this minus the cube root of 2 cubed times the cube root of 2. And the cube root cancels with the cube. And I'm left with 25 minus 2 cube root of 2. Now careful, make sure to write your indices as nice and small because you don't want them to get too big to look like a normal number in the front. Alright, and that's it. Let's take a look at the next example. Rationalize each denominator. Okay, what does that mean? Well, basically, whenever you're working with radicals, we're not allowed to leave a radical on the denominator. It's just a rule that mathematicians have created over the time. So that's what we're going to factor, or that's what we're going to practice doing. Now, there are two basic ways. The first one is if you just have a monomial on the bottom, so it's just one term. The second way is if you have a binomial, for example, a number plus or minus another number. Those have two separate methods for solving, so make sure to keep an eye out for that. So the first one is the binomial. How do we do this? Well, our goal is to find something to multiply, find a number to multiply, 2 root 7 to get a perfect square inside of that root. Why do I care about that? Well, remember, if we have a square and a square root, they can cancel. And then in the bottom, we would no longer have a radical. And remember, that's my goal. I want to get rid of the radical. So the question is, what can I multiply root 7 by to get something to the second power? Well, if I multiply root 7 by root 7, what would I get? Root 7 times root 7 is going to be square root of 7 squared. Hey, and look at that. That matches my index, which means they'll cancel. And if they cancel, I won't have a radical in the denominator anymore. So let's do that. We'll multiply the top and the bottom by root 7. Now careful, why am I multiplying the top and the bottom by root 7? Because it's the building up property. This is just an expression. I have to do that. So it'll be 2 root 7 all over root 7 squared. And now we have created the perfect thing, what we were looking for. That radical cancels with the 2. And we have 2 root 7 all over 7. Now once again, we only care about the radical being in the denominator. Since it's in the numerator, we're all right. And we're done. Let's take a look at B. This one's a little more complicated. You know what? It's usually easier if we simplify. So let's go ahead and break it down so you have the cube root on the top and then the cube root in the denominator. Well, what's the cube root of 8? That's going to be 2. That'll be negative 2 over the cube root of 2y squared. So now I'm trying to rationalize. I'm trying to get rid of that radical in the denominator. It has an index of 3. So I want to create something cubed so that I can cancel those guys. At the moment, I only have 2y squared. What can I multiply by 2y squared to get something cubed? Any ideas? Well, if I multiply 2, since it's only 2 to the first power, if I multiply it by 2 to the second power, I would get 2 to the third power, and that's what I'm looking for. And then if I multiply y squared by just y, I could get y cubed. So I would end up with 2 cubed y cubed. Alright, that is exactly what I need. Because when I get that, I'll finally get my 2y squared, or sorry, 2y cubed, and it would cancel. So let's do that. We'll multiply the top and the bottom by the cube root of 2 squared y, cube root of 2 squared y. Once again, why do we do that? I'm trying to create something that'll cancel with my index. Okay, so when I do that, I'll get negative 2 cube root of 2 squared y all over the cube root of 2 cubed y cubed. And I can rewrite that. Those cancel, and I'm left with negative 2 cube root of 4y all over 2y. And those 2's cancel, so I'm left with, running out of room kind of, negative 3, or sorry, radical 3 cube root of 4y over y. Okay, so we've done that. All right, let's take a look at the next one. Does this one look different? It does. This is the binomial case I was talking about, so we have to treat this differently. When we have a binomial case, what we're going to do is we're going to think about the concept of a squared minus b squared equaling a plus b, a minus b. If you remember, when you multiply out conjugates, the middle term is gone. And that would be really helpful for this. If I multiply this by the conjugate, so 4 minus the cube root. So if I go ahead and multiply the conjugate, do first outside, inside, last. First is 16 minus 4 root 3. Do the radicals cancel? They do. When I multiply by the conjugate, the radicals will cancel out. And that is exactly what I want. So my goal is to multiply my binomial by its conjugate. And when I do that, then the radical will cancel out, because one of the terms will end up getting squared, like so, and the radical will cancel, and then the other radicals will have like terms and they'll just cancel each other out. So let's go ahead and do that. So what's the conjugate? Well, I already mentioned it before, but it's the same first and last term, except you just change the sign. Once again, notice you change the sign. Okay, so then I get 2 plus x on the top, 4 plus root 3 on the top, divided by, and I'll go ahead and I'll get 4 squared minus root 3 squared. So what do I do? Well, on the top, I'm going to have to FOIL. So I'm going to do first, outside, inside, and last. And what do I get? For first, I get 8. Outside, I get 2 root 3. Inside, I get 4x. And last, I get x root 3. Divided by, well, 4 squared is 16, minus root 3 squared. Well, we know that those cancel, and I'm left with 3. So I have 8 plus 2 root 3 plus 4x plus x root 3 all over 13. And I can't simplify anything else. There are no like terms, so I'm done. That is it. All right, our last example. So what do we have here? We have simplify, write each quotient in lowest terms. So the first one, well, there's no radicals in the denominator, so I don't need to simplify that. I just need to make sure that there are no factors that I can pull out and cancel. You know what? I can. Careful though. You might be tempted to say we can cancel the 6 with the 6. Why can't we do that? Because in order to cancel like that, we need to be canceling for multiplication. And that 6 is being added, so we need to create a multiplication before we can cancel. And even before that, let's check our radicals. Can we simplify them? That's a root 8. I know there's a 4 in there. So let's go ahead and fix that. So that's going to be root 4 times root 2 all over 6. And that'll equal 6 plus 4 times, and this becomes a 2, root 2 all over 6. And we get 6 plus 8 root 2 over 6. Now can we simplify? Yes, we can go ahead and factor out that 2. And we can now cancel because there's multiplication going on. So the 2 cancels, and 6 divided by 2 is 3. And we're left with 3 plus 4 root 2 divided by 3. Sorry, a little squishy there, but hopefully you can read it. All right, let's take a look at the next one. So same thing, make sure we have the radical simplified first, and it looks like we have a square under a square root, and I'm pretty positive that 50 can be simplified as well. 50 is the same as 25 times 2, and 25 is a perfect square. All right, let's go ahead. Game plan. 15k plus, and that's going to be, I'm going to go ahead and separate it into the perfect and then imperfect values. 50 is 25 times 2, so I'll go ahead and write the perfects in here and the imperfects there. And then k squared, well, that's already perfect. That'll be k squared. So it looks like just the root 2 is by itself in the radical that can't simplify. And then let's go ahead and keep simplifying. So 25k squared is going to simplify to 5k root 2 all over 20k. Okay, so remember, before we can cancel, we need to create multiplication, so we need to factor. In the numerator, the top, what can we factor out? Well, both of these contain a 5, and they both contain a k. Let's go ahead and factor out 5k, and what's left over? From 15k, we're left with 3, and from 5k root 2, we're just left with the root 2. And now we can simplify because of the multiplication. So 5 cancels, and we're left with, well, 20 divided by 5 is 4, and then the k's cancel as well. So what are we left with? We're left with 3 plus root 2 divided by 4. And that's it. We're done.